Hello everyone, I'm Jesse Mason, and for this episode of Teach Me, we'll use Archimedes' principle to determine the maximum load a floating body can carry before submerging completely in a fluid. Here we're considering a number of 30-kilogram penguins on top of an ice float of known dimensions. As always, we start by drawing a picture. I'm going to draw a single penguin just because this one took so long to draw. And yes, I did look up how to draw a penguin on YouTube. This penguin standing atop a disc-shaped ice float somewhere in the water, so I'll draw some water here as well. Now, once we've drawn our picture, we need to identify and indicate our knowns and unknowns. I know that each penguin has a mass of 30 kilograms. I also know that the diameter of this float is 15 meters, and that the thickness of the float is 1 meter. Now, there are a couple of knowns here that are implied but not given outright, and those are the densities of seawater and ice, so I'm going to have to look those up. The density of seawater, I find, is about 1,030 kilograms per cubic meter, and the density of ice is 917 kilograms per cubic meter. Lastly, I'm going to indicate the thing that I'm looking for, the unknown, and that is the number of penguins, NP, that cause this float to submerge completely. Now we need to determine what sort of problem this is. At this point, a typical physics student has encountered only 4 types of problems: kinematics, Newton's second law, conservation of energy, and conservation of momentum. Since we've neither motion nor collision here, that means this is a Newton's second law problem, which means we need to draw a free body diagram. A free body diagram is a diagram which isolates a body from its environment, indicating only the forces acting on that body. The forces acting on our ice float are thus the weight of the ice itself, that is the force due to gravity, the normal force due to the penguins standing on top of the ice float, and balancing out these two forces is the buoyant force, due to the ice float being immersed in a fluid. Last but not least, we want to indicate our coordinate system. So now what we're going to do is we're going to utilize our free body diagram in the application of Newton's second law in the y direction. So we write the sum of the forces in the y direction is equal to the product of the mass and the acceleration in the y direction. Now, is our object in question accelerating? The answer is no. Why? Well, because we said so. That is to say, we are setting just the right amount of penguin on the ice float to perfectly submerge it, not sink it. So we can set this acceleration to 0. Next, we'll retrieve the forces from the free body diagram. In the positive y direction, we have the buoyant force. And in the negative y direction, we have the weight of the ice and the normal force due to the penguins, equals 0. Now our unknown, the number of penguins involved here, is buried in the term for the normal force due to those penguins. So what we're going to do is move the normal force to the other side of the equal sign. Next, we'll apply Archimedes' principle, and Archimedes' principle states that for a fully or partially submerged object, the buoyant force on that object is equal to the weight of the displaced fluid. So for B, we're going to write W displaced minus the weight of the ice is equal to, and instead of the normal force to the penguins, I'm actually going to write the weight of the penguins. Because that ice float's not accelerating, we can assume that that normal force is equal to the weight of those penguins. Now we're going to substitute in our definition of weight, mass times gravity, for each of these terms. So we have the mass of the displaced fluid times gravity, minus the mass of the ice times gravity, equals the mass of the penguins times gravity. Only for this last term, we're going to do something a little different. We're going to use the mass of a single penguin and multiply it by the number of penguins there to give us the weight of all the penguins on that ice float. That's how we're going to get NP. Now, we don't have the mass of the displaced fluid, nor do we have the mass of the ice. But what we do have are densities and volume vis-a-vis the dimensions of the ice float. So for the mass of the displaced fluid, we're going to use the density of the displaced fluid times the volume of the displaced fluid. And that's times G minus, and substituting for the mass of the ice, we'll have the density of the ice times the volume of the ice. That's times G equals MPG NP. Okay. Now, if you're like me, those G's have been bothering you since the last line, so we're going to divide those out. And this next part's key. Consider the volume of the displaced fluid and the volume of the ice. What is the relationship between those two quantities? Well, remember that we said we're going to have just the right amount of penguin to fully submerge our ice float, and that means that the volume of the displaced fluid is going to be equal to the volume of the ice. In other words, every cubic centimeter of ice is displacing a cubic centimeter of water. And while we're on the topic of volumes, we should note the volume of a disk. It's just pi times the radius squared times the thickness. Good. Now that we've determined that the volumes are identical, we can factor those out to the front here and use our expression for the volume of a disk. So we have pi r squared times h times the density of the displaced fluid, and we're going to go ahead and use the saltwater subscript because that is the fluid being displaced here, minus the density of ice equals mp/np. And now all we need to do is divide by the mass of a penguin to get the number of penguins that will perfectly submerge this ice float in the salt water. By the way, did you know that fossil records demonstrate that penguins have been around for 60 million years? We may laugh at their flightless flapping, but these tenacious toddlers survived the global extinction event that wiped out the dinosaurs. That makes the cute and cuddly penguin one badass bird. Anyway, we have all the values we need to solve this problem now. We have the radius, just divide the diameter in half. We have the thickness of the ice float and the mass of a single penguin, and the two densities associated with the problem. So all we need to do is plug this into a calculator. And when we do, we get 665.6 penguins. Now, I don't know about you, but I never seen 6/10 of a penguin walking around. Sorry, Chris, but the question is actually asking how many penguins will it support before submerging? And the answer to that is 665 penguins, because a 666th penguin, besides being bad luck, would cause the float to sink. So there you have it, Archimedes' principle, Newton's second law, and a very bad impersonation of Christopher Walken. I'm Jesse Mason. I hope this video was helpful to you, and until next time, happy learning.